It occurred to me that lots of people have no idea how an academic lab operates. I think people picture lots of nerdy-looking men in spotless white lab coats, putting colored liquids in test tubes, or writing on a clipboard in a sterile, ultra-clean environment. That's rarely the case. Much of the research in this country is done by people between the ages of 21 and 28, so it's a very young crowd. Many research labs, especially at universities, are likely to have a radio on. Stained lab coats are passed down from generation to generation, if they're worn at all. Most people will be wearing t-shirts, even though safety protocols prohibit shorts or sandals, they are present in abundance. There are dirty labs where no one takes responsibility to clean the bench tops, and there are compulsively clean labs where everything is alphabetized. There's a lot of meetings, joking around, office pranks, paperwork, wasting time, and late hours. In short, working in an academic lab is not that different from working almost anywhere else. I'm going to go through some of the key points of how an academic lab operates. First, the people. There's a hierarchy of sorts, but very few formal titles. Imagine each lab as its own very tiny research company. The boss is called the principal investigator, or PI. He or she will have the equivalent of a PhD or MD and decades of research experience even as a junior faculty. They might have the title of assistant, associate, or just professor. Some are very hands-on in their lab, and some have become more administrator than bench scientist. Their job is first and foremost to write papers and to submit grant proposals. Secondarily, they manage the lab's resources, personnel, keep people focused and on track, and many of them have teaching and office hour responsibilities. The 3 to 9 hours a week actually spent in lecture classes are really only the tip of a very large iceberg for an academic professor. A typical salary for a PI in the US might be between $55,000 and $95,000, depending on seniority in the institution, although in some cases it's possible to supplement that from grants, speaking, and consulting. The next tier down are the postdocs, also sometimes called research fellows. These are PhD scientists who are looking to build a reputation, so they can go looking for a faculty spot and a lab of their own. Some write their own grants, and all write their own papers. Generating data and producing papers is what these guys do. They should expect to publish at least 2 papers a year. A postdoc could be anywhere from 2 to 5 years, and some people do multiple postdocs. They are the senior folks in the lab, and generally have a deep mastery of the topic they work in. You will find them at the bench, writing papers or reading papers. Pay is highly variable, but a typical range might be $35,000 to $50,000. There are also grad students, sometimes called Graduate Research Associates, or GRAs. While they work on their degree, they are expected to produce useful data and get at least some of it published. They are usually given their own project with some supervision from the PI or a postdoc. They're still developing some skills at the bench, and they also have to take time to study for classes. Some are given teaching assistant responsibilities, the so-called TAs. They make less than $30,000 working 30 to 50 hours a week. Lastly, but not least, are the technicians and specialists, administrators and student workers. Some labs hire professional technicians to maintain some stability in the lab and take over some of the mentoring from the postdocs. Some have administrators who manage the grant accounts, do the purchasing, and so forth, or the college department may furnish these resources in common. Some institutions have core facilities containing equipment too expensive for a single lab to purchase or maintain, with on-staff personnel to manage the core equipment. For example, a licensed veterinarian may be employed to supervise a large animal colony. Salary is commensurate with experience, education, and responsibilities, but don't expect to make as much as a PI in most cases. Where does the money come from? The major U.S. granting institutions are the National Institutes of Health, which primarily funds biomedical and basic biology research, the National Science Foundation, which funds a much more broad scope of studies, and the Department of Energy, which focuses on certain specialized areas of bioinformatics, genomics, and alternative energy. There are other smaller sources of funds, the EPA, the USDA, but by far the largest is the NIH. They disperse what are called extramural grants in the order of $15 billion. Compare that to the top pharmaceutical company, Pfizer. Globally, Pfizer spends $8 billion in R&D every year. As opposed to extramural grants, intramural grants are dispersed to just the agencies of the NIH, which includes the National Cancer Institute, National Institute of Allergy and Infectious Disease, National Institute on Aging, and so forth. A typical NIH grant is called an R01 grant, which is usually for a few $1,000,000 over 1 to 5 years. That sounds like a lot, but you need to pay salaries and benefits, purchase equipment and reagents to produce data, and don't forget the large chunk that the institution takes out, called overhead and indirect costs. At some universities, this can be 30 to 40% of the grant amount. To keep the lab afloat, the PI needs to keep the grants coming in. To do that, they need to demonstrate that they are capable of producing useful and meaningful data. The people in the lab produce the data by running experiments to test hypotheses, at least in principle. In reality, the process is very dynamic. You can go on fishing expeditions, or screen a lot of possible targets for useful clues about what's going on. The results of one test might get you no closer to a conclusion, but might open up additional avenues of inquiry. The formal scientific method is rarely used in a vacuum. Scientists have hunches, they follow them, and adjust their hypotheses accordingly. Most labs will have staked out an area of specialty that is extremely narrow, a single virus or a single cellular pathway, or a particular disease or organism. This maximizes grant writing success because it's easy to establish yourself as a world expert when you have a very narrow focus for your research. This also prevents competition between PIs who came from the same lab. Each can stake out a particular aspect of their problem without competing for the same discoveries. This is strictly a casual honor system, and if a lab comes up with an exciting result outside their area of expertise, you can bet they'll publish it, no matter how many colleagues' toes they step on. The view of science as a utopian communistic pursuit is rarely the case. Competition is the norm. Competition for publications, grants, and recognition.